So welcome to power system classes. So we were in the last class we were looking at the Vibus and the ZBus. So I have described how to do the Vibus for different configurations and what is the advantage. So what are the things you should take care while we are actually considering the Vibus. And I have discussed about the Cron's reduction technique. How can we actually remove one one base one node so that we can make it one node less. Okay, like all the things I have covered. Now we can go to ZBus. Okay. We can look at the ZBus. So I have already explained that ZBus is basically Vibus inverse. Okay, so I will just share the screen so that you know. Okay. I hope you can see the screen. Okay. So Vibus is basically ZBus inverse. So I have already mentioned the last class. The number of buses become very, very large. And buses become very, very large. Then Vibus will be sparse, right? But if the Vibus will be sparse, that doesn't mean that ZBus will be sparse, right? That means ZBus will be full matrix. Like inverse of a sparse matrix may not be a sparse matrix, so it can be a full matrix also. So that means the Z matrix here will become a full matrix. Okay. So it is not advisable to invert Vibus to get ZBus. Right. I have already explained in the last session why we should not invert Vibus to get ZBus, because if we invert Vibus, because the inversion is of order into. Okay. So the order of complexity is very high for inversion. So we have to find some other method to find the ZBus. Okay. So what is basically the definition of ZBus? So we can define ZBus like this: V1, V2, V3, etc. up to Vn, Vb, Z11, Z12, Z1n, Z21, Z22, etc. up to Z2n, Zn1, Zn2, etc. up to Zn into I1, I2, etc. up to In. Right. So this is basically the equation for ZBus systems. Now, what is basically Z11? So Z11 will be V1 by I1 at I2, I3, etc. up to In is equal to 0. That means it is the impedance, driving point impedance V1 by I1 at all other currents are actually open circuit. So if all the currents are actually open circuited, then what is the current seen at the input terminal? So Z11 is also known as driving point impedance function. Okay. So this is basically the input terminal, and where Z11 will be equal to V1 by I. Okay. Similarly, we can define Z12, so that will be V1 by I2, right? At all other currents are actually 0. This is not exactly the driving point, so it is actually something like a transfer. Okay, transfer resistance we are measuring. We are giving voltage at V1 and we are measuring current at I2. Okay. Like this, that will be basically Z1. Okay. Similarly, we can actually find Z1n, that will be V1 by In at I1 comma I2 comma etc. to In. So this is basically the definition for Z matrix. Okay. So that means what I'm saying is Z11 is not equal to Y11 inverse, right? This is not correct. Okay. Z11 is not equal to 1 by Y11. Okay. So if I already know Y11, just take 1 by Y1, that is not equal to Z1. Okay. But, so I think you understood, because a matrix, if I take the inverse of a matrix, it doesn't mean that each each number will have a, that is not correct. Okay. So I hope you understand. You can just write down these things and we can move forward. I'll give you 1 minute time so that you can actually write all this. Okay. Now we can go to the important part of this one, that is basically known as the Z-bus building algorithm. Okay. So what is basically Z-bus building algorithm? So in Z-bus building algorithm, what we normally do is actually we have to use this algorithm for creating the Z-bus. So there are 3 or 4 cases. Like normally there are 4 cases. First case is adding ZB from a new base P to reference bus. Okay, I already mentioned the last session what is basically reference bus. Now we have something like we have a power system is there, subsystem is there here, and some reference bus is there, and we are actually adding a new impedance ZB from a new base P. Okay, this is actually what is. So if you check that, this is basically reference, right? So the current will be actually flowing only through this bus. So we already have the Z bus of this particular network. So if you know that, so I can write like this: V1, V2, V3, etc. up to Vn. So this bus is already available in this particular network. Now we will be connecting a new bus, that is Vp. Will be equal to. So we have to keep the old matrix as like that. So this will be our old matrix, that is Z bus old. Then we have to actually put some rows and columns over here. So since we are actually connecting to a reference bus, so the current will not have any effect on the other buses, right? Because this will actually directly flow from this bus to this bus. So that means this can be written as 0, 0, 0, etc. Up to here we will be actually setting. Since this is a symmetric matrix, we can actually put here also 0 into I1, I2, I3, etc. up to In, then I. So this can be also because this is the reference bus, right? This is basically Vp. If you write the KVL here, sorry, KVL Kirchhoff current law here, Vp minus 0 divided by ZB equal to Ip, right? Sorry, ZB. What we are actually connecting ZB. So that means Vp equal to Ip into ZB, right? That's all. That is actually we are getting from here. So in the Z-bus building algorithm, if a new bus is connected into its reference bus, then what we have to do is we have to add the reference new bus at the end of the Z bus and put a row and column. So except the last column, put everything 0, and here also except the last row, put everything 0, Then add the last row and column, the n plus 1 the term. Okay, comma n plus 1 the term z0. Okay, this is the new bus, new z bus. Okay, this is very simple. Like assume that this is a reference bus, and we are actually adding something here. So keep the old z bus like this, and 0 0 0 0 J3 or something here. Here also 0 0. This will be the new z bus. Okay, so this has to be used like for constructing the z bus. Now the second case. Case 2, adding ZB from a new bus B to an existing bus K. Right. So we have a power system here, and this is the reference bus, and this is another bus. Okay. So this let this bus be K. This is not the reference bus. This is the reference bus R. Now we are connecting a impedance ZB, and we are connecting. But here this voltage is actually not a reference, right? So this voltage is actually depending upon all other voltages also. So there might be current flow through all. So these elements are not exactly 0. So we have to find this. That is Vk new will be equal to Vk original plus Ip into Zkk, right? So there will be a rising potential at this particular point. Okay. So this is basically KVL. So we can write Vp equal to Vk original plus Ip into Zkk plus Ip into Z. Right. Because this voltage Vp here will be this plus this one, right? So that is basically what I have written here. Now we can write Vp will be I1 into Zk1 plus I2 into Zk2 plus etc. up to In into Zkn plus Ip into Zb plus Zkk. Right. Just what is the Vk original? I have just written it. Okay. So we can just expand this. So that means now what we are getting is the new Vp is having all the terms, right? Because it depends on I1, it depends on I2, and it depends on In, and it depends on Z. Depends on all this. So how we can write the equation? So V1, V2, V3, etc. up to Vn. Right. Now Vp. Now we have a Z bus original. Right. This is the old one. Now we have to add Z1k, Z2k, Z3k, Z4k, etc. The last one will be ZKK plus ZPK. Sorry, ZB, what we are actually adding. Okay. Now similarly here also Z1k, Z2k, Z3k, like this. Okay. Into I1, I2, I3, etc. up to I. Right. So these things you have to actually look. So what we have to do here is, so we can write like this. I will explain this slide. Okay, so we already have a Z bus. Okay, like this. So for your information, I will just A, B, C, D, F, H, I, J, K, L, N. Okay, like this. This is the first bus, second bus, third bus, and fourth bus. Here also 1, 2, 3, 4. Right. So we have 4 buses here, like this. This is actually everything is interconnected like this. Okay. Now we are continuing a 5th bus, which is connected to our 3rd bus. Okay. So we have to take the 3rd row. Okay. And 3rd column. Right. This will be the 3rd row and 3rd column. Now you have to create a new matrix, right? So for that, you have to keep, so now it will be 5 by 5, right? So you have to keep this one similar here. That will be, this will be that 4 by 4 matrix. Just keep this here, 4 by 4, right? Now what you have to do is, this is basically here, 3rd one, right? So take the 3rd row here, this one, Z1K, right? So this is basically Z13, take it here, Z23, Z33, and Z43. Now here we have to add Z33 plus Z, that is K plus what we are actually continuing, the impedance be ZB and K plus Z. Then here also just take the 3rd row, C, G, K, O. Okay. So like since this is a symmetric matrix, this E will be equal to B like that. Okay. Okay. So I will just erase it and I will make it symmetric. This will be A, E, I, M. Right. This will be J, N. Right. So here also. So this will be basically J. Will be, I just make it symmetric. That is. Oh, right. Okay. So I, J, K, like I, J, K. Here also it will be I, J, K. Right. So similarly, like this, we have to actually modify it. So here, so I think you understood this one. Okay. Okay. Now the third one is, this is case 2. Okay. So the third case is adding ZB from an existing bus K to the reference bus. Right. So here, what is happening is no new buses are added, right? But there is initially this is a bus K, this is reference bus. Something was there. Now what is happening is we are adding one more thing here. That's all. Okay. So this is what is actually happening. So now we can write result bus new equal to result bus old minus z h of n plus 1 to z n plus 1 of I 5 zkk plus z. Okay. I will just explain what all these things. ZB is the new impedance connected. Okay. and it is connected between existing bus K, right, and reference. Okay, so like this, we can actually find this. Okay. Now, next one. Adding Z bus between, sorry, adding ZB between two existing bus J and K. So that is, we have a power system here. Then there are two buses, okay, J, K. This is all actually part of this power system. So this is actually connected here. This one is also connected here, right? Now we are actually connecting a new ZB. Right? So how will the new matrix looks like? Okay, that's what we have to find. So it will be like I will be just writing V1, V2, V3, etc. up to Vn, then 0. Okay? Because there are no new buses are connected, right? So the dimension cannot increase. So Z bus old. Then we have to. So here it will be ZB, what we are actually connecting here. Then we have to keep like this. ZJ1 minus ZK1, ZJ2 minus ZK2, like this. Well, here also Z1J minus Z1K, Z2J minus Z2K, like that. Okay. So somewhere it will be like this: ZJJ minus ZJK, then ZNJ minus ZNK. Right. So like this we have to find it. So example I will show so that you will understand. Similar example, okay, what we are at. A, B, C, D, C. Okay, like this. And this is the first bus, second bus, third bus, and fourth bus. Here also one. Second bus, third bus, and fourth. Now we are actually connecting a new bus between 2 and 3. Okay, just assume that it is between 2 and 3. Now the new Z bus will be, take the old one that is here. Okay. Now here we have to put Z this minus this, B minus C, then E minus F, then F minus H, then G minus I. Right. So here also we have to type like B minus C, E minus F minus G minus I. Then what we are connecting, that we, this is the old 4x4. So this will be actually coming here. That is equal to V1, V2, V3, V4, then 0 into I1, I2, I3, I4. Now the new one, that is IP. Okay. Now we can use a Cron's reduction because this is 0, right? So we can represent IP as a function of all this, and we can make a 4x4 matrix. Right. So that will be the exact Z bus for this particular. Okay. So this way we can actually build the like actually we can use this is something known as the Z-bus building algorithm, right? So we can use this algorithm for making the Z-bus. Okay. From scratch, actually, you can make it if you like. That's a. I think you have already studied all these things for a great preparation. I'm just like giving how to do that. That's all. I'm just not going to numericals. You can actually check the numericals because I have to solely like I'm just wrapping just giving you a insight of what is actually happening. Okay. So this is how we can actually create the Z-bus from using the Z-bus building algorithm. Okay. Now can write this, and we'll be moving to a next topic because the second part of the power system analysis will be load flow studies. You can write down this one, and we can move to the load flow studies after this. Okay. So some places it is known as load flow or power flow studies. Okay, like both actually we can use. So why we require power flow or load flow? So the importance of load flow is that it is used for planning of load. Okay, because assume that there are some places we need power at these places, and this is having a generator here, and some places we are having another generator. So everything will be actually interconnected, right? So we have to find how much power is actually drawing here, power is coming here. We have to find all the voltages at what is the particular bus and everything. So we have to actually plan the system, right? The system has to be planned so that it will help in flowing the power from one point to another. Second one is the future expansion. So how much load can be extra added here so that this voltage will be in particular range. So all the mathematical calculation related to voltage and load and everything actually can be found from the load flow studies. Okay. Then to find the best operating point or best operation, to find the best operation of existing system. That is how much power is actually flown from here to here, then here to here, like that. So we have to find the best and optimal actually solution for this particular problem. Okay. So these are the important aspects why we require a load flow studies, and what is the output of load flow studies. What is the output of load flow? Okay. So the basic thing with the output of load flow is the voltage at all the buses. Voltage at all the buses. Then angle. angle of voltage at all the buses, then P and Q. That is real and reactive power at all the buses. Right. We have to find what is the voltage at this particular bus, and we have to take the angle of that particular bus, and what is the P and Q. That is, P demand will be there and P supply will be there. So, it should be made equal. So in a bus, actually, if there is something like a load is connected here with some 1 per unit or something, 2 per unit, load demand is there, then this bus should supply this particular load. Okay. So that's why. So we have to make sure that this, this system should operate such a way that the demand of the power in this particular thing should be actually satisfied. Okay. That's why we are actually doing this power flow studies. Now we can check about what are the different types of buses. Okay. This is very important in a load flow study. The first type of bus is known as load bus. Okay. In load bus, we specify P and Q. Okay. This is also known as a PQ bus. Load bus or a PQ bus. Here we have to find V and delta. Right. You have to find the voltage at the particular bus and delta. That is the load angle of that particular bus. We can wait for a minute. So the second type of bus is known as generator bus or PV bus. Generator bus or PV bus. Here P and V will be specified and Q and delta we have to find out. This is basically specified. This we have to find out. The third one is known as the slack bus or swing bus. Okay. So here we are actually only specifying the voltage V. PQ are normally not specified because the slack bus is basically used to compensate the losses that is happening. Losses happening between the transistors, right? Because nowhere in the load flow studies we are actually taking the losses in the system, right? Because we are actually caring only about the how much power it has to supply to the load, right? Or how much power generated has to be taken. So in order to taken care of the other things like compensate the losses and this slack bus will be actually taken as the reference. So it will be taken as the reference bus, and normally it will be angle will be 0. So with respect to this angle, we will be finding all other angles. This is also known as a reference bus. So this voltage can be taken as 1 angle 0. So all other voltage and all other delta is actually finding with respect to or within the reference to this particular bus. Okay. So I will be explaining these things again. What are the different types of buses? So this will be load bus will be there, generator bus will be there, slack bus or a swing bus or a reference bus is there. So here we are actually finding P and Q. So P and Q are specified. We have to get this much of P and this much of Q. So with respect to this, we have to find V and delta of that particular bus. So generator bus is there because if a generator is actually connected to a particular bus, the voltage of that particular bus is already known, right? Because the generator is already connected. It's basically PV bus. So this voltage and the real power will be specified here. Yeah, because the voltage and Q is actually related. If you study a synchronous machine, so the voltage control is actually happening through the reactive power control, right? So we don't specify both. One is specified because both cannot be independently specified because both are dependent. So if PV is there, then Q and delta we have to find out. Then slack bus we actually will be taking this reference and we are actually specifying V and delta. Here we have to find P and Q, right? So this P and Q will be actually used to compensate the losses, right? Compensate the losses. So this is how actually we are using the, we have to find all the voltages. So what is the outcome of a load flow study? What is the outcome of load flow? That is, we have to find all the voltages and its corresponding angle in all buses. Then find P and Q. That is real power and reactive power in all the buses. Okay. So in some places the voltage is already specified. In the case of generator bus, then we have to find the other things, P and Q and delta. In some places P and Q are specified, like a load bus, then we have to find V and delta. Okay. So at the end of the load flow study, we will get a table with all the things. Okay, what is the reactive power of that particular bus, real power of that particular bus, then what is the voltage at that particular bus, what is the angle at that particular bus. So everything will be actually, we'll get at a table at the end. Okay. Now this is the outcome. Okay. So what is the input for the load flow study? The inputs are basically our system, right? In that particular system, actually we are studying the load plus or the load flow. So the Vibus is required. So Vibus is basically gives the interconnection between different buses, how the with what impedance these buses are actually interconnected, right? Hence Vibus is required for finding the load flow state. Okay. Then at if it is a PQ bus, we have to find what is the, you have to give what is the exact P and Q, what is the load demand at the particular point. Then if it's a PV bus, we have to give the P and Q, V. But in most of the places, there will be some Q min and Q max. Okay, because for the voltage control, this Q min, actually this Q should not be less than or should not be above the Q min and Q max. So like that, it should be less than Q max and should be greater than Q min. Okay. So this we have to take care of that. Okay. So these things we have to, this is the input thing, Vibus and all the demands and supply will be given as the input to the supply. Then we have to actually find out V, delta, P and Q, corresponding P and Q, which actually satisfies all these conditions. So that's how we have to flow a load. So load flow is basically an iterative process. Very simple only, like we have to solve a set of linear equations, but we have to, it is not a straightforward, just enter something and you get result, but we have to follow the iterative. There are two methods what we normally use. The first one is a Gauss-Seidel method. Second one is basically Norton-Raphson. Okay. So these two methods, I'll be teaching you these two methods. So you have to like, you have to write all these things, and we'll be actually looking at Gauss-Seidel method in this particular session. Okay. Okay. The first thing you have to remember here is a load flow problem. A load flow problem. Okay, let's wait. A load flow problem is always a well-posed problem. Right. So well posed problem in the sense we have enough number of equations already there. Okay, like we don't want to think about it like the system is overdetermined or underdetermined. We will be having enough number of equations with the one, but we have to manipulate it. Okay, we have to manipulate it in such a way that all the given conditions are satisfied. That's all. So it is almost like a iterative problem, but we don't want to worry about overdetermination or underdetermination of the variable. Okay. So in Gauss Seidel, what we normally do is we will be expressing the voltage of a bus as a function of its real power and reactive power and network parameters. Right. I will be explaining this statement. This is the most important part of the Gauss Seidel. Expressing the voltage of a bus as a function of its real and reactive power and network parameters. Okay. So I can write like this: V2 into taking second bus. Okay. Because first bus is actually considered as slack bus, so we don't write that. So second is. So assume that it is V2 into I2. Okay. So start with second. So V2 into I2 is basically V2 plus JQ, right? So this is basically the power balance equation, right? So V into I star, that is basically the complex power V2 plus JQ, right? Now, what if I take the conjugate of this one? So that is basically V2 star into I2 will be equal to P2 minus JQ, right? So why I am concerned about it's the most important question in this particular domain. Why we take V2 star? Because why can't we take I2 star? Because in most of the cases, this angle is very small. It is very easy to do this way than actually taking I2 star, because I2 is almost it's a way unknown. So if I take star, then we have to take the star of all the things later. So, but V2 is actually the voltage. So if we know the V2, then V2 star is also easy to take than I2 star. That's why we are actually taking the conjugate of this one. So, so this only for mathematical simplicity, because we can actually simplify the expression. Right. This is basically mathematical simplicity. So we can write V2 star into I2, basically V2 plus JQ2. That means I2 is basically V2 minus JQ2 by V2 star. Right. That is basically I2 here. But we know that I2 is basically Y11 V1 plus Y12 V2 plus Y13 V3, etc. up to Y1n Vn. Right. Sorry, Y21. This is I2, right? So here comes the mathematical simplicity. So if I take I2 star here, we have to take the star of all the things. That is very complicated, right? So instead of that, we are actually taking the I2 only here. That means we can directly substitute it here. Okay. That's where the mathematical simplicity is actually comes. So I hope you understand now. So if we substitute it together, these two equations, what we are getting is B2 minus JQ2 by B2 star is basically Y21 V1, Y22 V2, Y23 V3, etc. up to Y2n Vn. Right. So that means V2, from here actually we can find V2, right? It's 1 by Y22 into V2 minus JQ2 by V2 star plus, sorry, minus Y21 V1. Now this Y22 which is already coming here, right? So we have to remove that. So plus Y23 V3 plus etc. up to Y2n Vn, right? Now now you can check here. So V2 depends on the circuit parameters Y21 and everyone and P2 minus J2. So similarly, we can write for all the equations, right? So Y3, V3 we can write, V4 we can write, V5 right? So almost up to Vn. Similarly, here also we can write everything here. And here these things are actually specified, P2 minus JQ2. Okay. On some places Q is specified, so we have to write Q in terms of V. Okay, like that I will be explaining later. So we'll get a set of equations like this: V1, V2, etc. up to Vn. Right. Set of equations are there that can be represented in this particular form. Okay. So we can write Vk as 1 by Ykk into Pk minus Jqk by Vk star, right, minus sigma n equal to 1 to n not equal to k, right, by kn Vn. Right, so this equation can be represented as this particular form. Now we can actually consider some initial values for V1, right? So we can take some values, so we can take everything as 1 angle 0 or some initial values, some initial guess, and that can be substituted here, right? Then we will get a new value of Vk, right? So use the new value of Vk and all the values of Vk, find Vk plus 1, then Vk plus 2, like that. Okay, like this. Okay, something like that. So now use the new vector to compute it again. Iteratively, we can actually solve this again. So at some place, you will reach something like this. So Vk plus 1 in the pth iteration minus Vk plus 1 in the p plus 1 iteration will be less than or some condition epsilon for all the bus. Okay, like not only for one bus, it will be for all the bus. At this particular condition, you can stop the iteration. Okay, so that is basically known as the convergence criteria. So in all the buses, like if there are 10 buses, then we have to find some iteration, pth iteration is there. So Vp plus 1 for any bus k minus Vp for any bus k should be less than some epsilon, or that the epsilon will be 10 raised to minus 6 or 10 raised to minus 8. So the mode of this is very, very close. Or then the two iteration, if the values of the voltage for all the buses are coming very, very close, then we can actually stop the iteration. So here we will get the stopping criteria for all the voltages. In some buses, like what you are getting is Q. There will be actually specifying Q. Now from the voltages what we are getting, we have to find the Q. So Qk will be minus imaginary part of Vk star to sigma n equal to 1 to n current. So Ykn Vn, right? So this is basically V into I, right? This is basically equation for I. So once you find all the voltages, then check Qk, and if Qk is not converged, then do it again. Okay. So until all the voltages and Q is also converged, because in some bases the Q will be specified, right? So some PQ bases the Q will be also specified. So we have to check about this Q also. Okay. So in this way, all the things that is V should be converged and Q should be converged. Or if like in PV base or something, we have to think about Q also in some places. And in some places, the Q should be less than Q min and Q max. And once all the voltages are converged, we have to actually take the Q and we have to check whether this Q min between Q min and Q max. Else we have to do the iterations again. So that it will be in that particular range. So this is how we have to actually do the Gauss-Seidel iteration. This is very simple only, like you have to code it, that's the important part. So here you are getting a set of algebraic equations. Okay. Set of algebraic equation is there. Take some initial guess, then update the first one, then you use the first one and all the initial guess, find the second one, then use the first two, find the third one. Like that, we can actually have an iterative process. Okay. So then we have to check the first stopping criteria. So when the values in the two iterations are very close, actually we can stop the iteration. So that we will get the voltage at all the values. The voltage will be a phasor, so we will get voltage and the particular delta together. Okay. We don't want to find it separately, so both will be actually we can get together as a phasor form. Okay. So if Q is also specified with this value of voltage, we have to find the Q also. Okay. So in this equation, we can actually find that. Okay. So by this, Gauss-Seidel part is over. Now in next class, we can move to the Newton-Raphson method. Okay. Because the main drawback with the Gauss-Seidel method is that it requires lots of iterations to convert. It requires lots of iteration to convert. So we have to find some method by which the number of iterations are very, very small. So first we will study the Newton-Raphson method. Then we will be going to look at the fast decoupled study. So these two things are actually very important because the most important part of a this Newton-Raphson method is that it is a Newton-Raphson method is a differential derivative based method. So derivative based, what is the important aspect of a derivative based method is that the convergence is very, very fast. Because the convergence is happening through the derivative, because derivative is where we get to the maximum slope or minimum slope, like that. So we'll be actually moving through the place we have a maximum slope, right? So something like this. There's a hill is there and this is the maximum slope. So if we actually slide through the maximum slope, we will reach this like more in the solution very, very fast. So that is the policy actually we are using the derivative part. Okay. We will be looking at the point where we have the maximum slope. So something like that we'll be actually looking at. Okay. So what is the advantage of having advantage of Newton-Raphson method is that this will actually converge very fast. Okay. Newton-Raphson method converges fast. The disadvantage of Gauss-Seidel is that this will take lot of iterations to get the results. So that's why we are not using Gauss-Seidel method and we will be actually focusing on Newton-Raphson. Okay. So we can see in the next class. I hope you understood these things. And next class we will be looking at the Newton-Raphson, and with that we will be actually closing our discussions on load flow. Then we will be looking at the economic load dispatch. So after economic load dispatch, we will be looking at the like faults, fault and other aspects. Then we will be looking at the transients. Okay, that is the most important part. That is the critical clearing angle and all the things. We will be looking at that things also. And at the end, we will be looking at the different fault analysis. Single phase, this fault, single line to ground fault, line to line fault, three phase fault, and all things that we will be looking at the end. So by this, almost all the things with the very very small way, actually we will be covering all the aspects of the power system. Okay. Thank you. We can see in the next.